In this one, I'm going to prove that if b and c are odd integers, then x squared plus bx plus c equals 0 does not have integer solutions. Now our domain is the integers. All right, to prove this, I'm going to need all of these facts that I have off to the side. Now, I'm not going to give a formal proof for all 9 of these facts, but I will show you why each of them are true. And so what I'm doing now to show you that they're true, you can think of this as something called a proof sketch. Okay, so let me sketch out the proof for 1. 1 says, if x is an even integer, then x squared is even. Okay, so if x is even, that means x equals 2k, where k is an integer. So that says that x squared is equal to 2k squared, which is 4k squared, which is 2 times 2k squared. If k is an integer, so is 2k squared. So x squared is even. Let me establish 2. If x is odd, x is 2k plus 1, where k is an integer. So that means that x squared is 2k plus 1 squared, which is 4k squared plus 2 times 2k plus 1. We can factor out a 2. We have 2k squared plus 2k plus 1. If k is an integer, then 2k squared plus 2k is an integer. And so then we see that x squared is 2 times some integer plus 1. So that establishes 2. If x is odd, then x squared is odd. Now let's do 3. An even times an even is an even. Okay, so let's see. Let's say you have an even, 2k, times another even, 2m. This gives you 2 times 2km. If k and m are integers, then 2km is an integer. This proves 3. Now for 4. Now, please take note that what I'm doing for explaining why each of these necessary facts, 1 through 9, are true, is not a formal proof. What I'm doing here is I'm just explaining quickly why they're true. If you wanted to, you could write up a complete proof for all of them. The essential piece of the proof for 4 would be something like this. You'd have 2k times 2m plus 1. Right before that, you would have x times y is equal to this, right? You'd have something like that. xy is equal to that, where you said above, you'd say, well, suppose x is even and y is odd, so x equals 2k, where k is an integer, so y equals 2m plus 1, where m is an integer, and then we go so on and so forth. But the essential piece is really this part right here. Now, if k and m are integers, then that means that 2km plus k is an integer. So this establishes 4. If you multiply an even integer and an odd integer, you get an even. If you multiply an even and an even, you get an even. That was 3. Okay, 5. An odd times an odd. So 2m plus 1, 2k plus 1. Let's see, this is 4mk plus 2m plus 2k plus 1. This is 2mk plus m plus k plus 1. So if m and k are integers, then 2mk plus m plus k is an integer, and this establishes 5. If you multiply two odds, you get an odd. Okay, 6. If you negate, so let's say you have an odd, 2m plus 1, and you make it negative, this is negative 2m minus 1, which we could write as 2 times negative m minus 1. Plus 2 minus 1. No, minus 2 plus 1, right? Minus 2 plus 1. Minus 2 plus 1. Okay, so negative 1 is the same as negative 2 plus 1, right? So that's what I did there. And now this is 2 negative m minus 1 plus 1. If m is supposed to be an integer, then negative m minus 1 is an integer. And this shows that the negative of an odd is still odd. Now let's look at the negative of an even. This is 7. Negative 2k, this is 2 times negative k. So if k is an integer, then negative k is an integer, and this establishes 7. Moving on to 8. So an even minus an odd is an odd. 2k minus 2m plus 1. Here we have even minus odd. This is 2k minus 2m minus 1. This is 2k minus 2m minus 2 plus 1 again. Remember, negative 1 is negative 2 plus 1. This is 2k minus m minus 1 plus 1. All right, so an even take away an odd is again an odd. All right, and lastly, number 9, an odd minus an odd is an even. Oops, odd minus odd, let's see, that would be something like 2m plus 1 minus 2k plus 1 So that establishes 9. Now we're ready for the actual proof. Now I don't mean to say that what I did to establish these facts, 1 through 9, are formal proofs. Remember, those are not formal proofs. What I will give now is a formal proof, and I will use facts 1 through 9 to help me out with it. Okay, proof. We're going to use a proof by contradiction. So we're going to say, suppose for contradiction that x is an integer solution for x squared plus bx plus c equals 0. Okay, x is an integer. We're supposing for a contradiction, we're going to find a contradiction, that x is an integer that solves this equation, x squared plus bx plus c equals 0. All right, so x is either even or odd. X is even or odd, right? All integers are either even or odd. So this brings up two cases. Case 1. X is even. If x is even, then x squared is odd. Oh, not odd, even, right? This is by 1, right? This is 1 right here. If x is even, then x squared is even. So, right, we assume that x is an integer solution for this equation. Well, if x is an integer, it's either even or it's odd. Well, let's see what happens if it's even. If it's even, then x squared is also even. We established that. X squared is even. So an even integer equals x squared, which equals negative bx minus c. What I've done is I've moved this bx plus c to the other side of the equation. Subtracting bx, subtracting c, we get to the other side of the equation. Now, remember, b and c are assumed to be odd. B and c are assumed to be odd. That's one of our assumptions. B and c are odd. Right, so if b is odd, then by 6, negative b is odd. And x, we assume, is even. Remember, an even times an even is an even times an odd is even. So this is an even here, minus, and c is an odd. We have odd. An even minus an odd is an odd. That's a contradiction. If x is an integer solution that is even, we find that an even equals an odd. That's a contradiction. Okay, so in case 1, if x is even, we find a contradiction. I don't have a lot of extra room here. Maybe I have a little bit. Let me see if I can fit this in. Well, okay, so case 1, x is even, we find a contradiction. We find the contradiction that an even equals an odd. That can never be true. Now, the work here I just erased, right? But I did go through that work for you to show you that work. Okay. Case 2. X is odd. Well, if x is odd, then x squared is odd. This is 2. If x is odd, then x squared is odd. So we have an odd equal to x squared, which again is equal to negative bx minus c. Now x is odd. X is odd, right? This is odd, and negative b is odd. Right, so here we have 5, where we have an odd times an odd is an odd. So we have odd minus c. C again, it is an odd. Right, this is one of our assumptions again. C is odd. And we have odd minus odd, which we've established is even. So again, we find another contradiction. Right, we have that an odd is equal to an even. Again, a contradiction. So, in either case, we get a contradiction. So our original supposition must be false. So x cannot be an integer solution. Since x cannot be an integer solution, and we didn't say what x was, right? We didn't say which odd x was. So there are no integer solutions. And that's the proof.